everyone. I'm Sharon Abhigna, your host for the day, and I'd like to warmly welcome you all to today's webinar by Vishay for Intro to Resistor for EVs. We do have Ms. Gulchan Armagan, Mr. Adrian Michael, and Mr. Clinton Stifler, who would be speaking with us today from Vishay. We firstly have Ms. Gulchan Armagan here with us. Welcome, Ms. Armagan. It's so nice to have you here. Please, Ms. Gulchan Armagan is the Director of Product Marketing, Vishay Nonlinear Resistors, who has been in this field for over 25 years. She completed her master's in electronics engineering and in business administration. Before joining Vishay, she served as a project manager for a large engineering company. It's a joy to have her here speaking with us on nonlinear resistors for EV automotive applications by Vishay. Welcome, Ms. Armagan. Over to you.
Thank you very much, Sharon. It's a pleasure to be here and to have this live webinar and to have with all the participants, all the guests. Let me share my screen so we can start immediately to learn more about the nonlinear resistors and especially about the NTCs. So today's main topic is about the thermistors especially on the EV applications, e-mobility in a more general way. It is a very current, trendy subject that as a Vishay thermistors, we are part of it. We are proud to be part of it. We are mainly, if you look to our components, we are making solutions for the onboard chargers, for the battery management, for the DC-DC converters, power inverters, but also on the LED lighting. These are the main structures that you can find Vishay thermistors in all type of e-mobility solutions. The main functions we are proposing with our thermistors are, of course, temperature compensation, sensing, control. How about when the voltages are elevated, what we do if there's an over temperature protection problem in rush current limiting, safety discharge. These are the design engineers' main questions. And we believe our components, the Vishay thermistor components, give the best solution by providing to those questions, those main questions of the designers. We have several components, as you can see in the below here, from SMD type to the leaded types, several leaded types, and we have also several sensors. So we call it a customization. We provide solutions to our customers based on different requirements. We will come back on that. But also we have a quite unique product, which we call it wire bondable, sinterable product, which will be a good solution for IGBT power modules, for example. And again, another unique product within the Vishay portfolio, it's a platinum sensors. These are linear products. They are not non-linear as NTCs or PTCs, but they are linear. So these are also used in many applications in the EV cars. And then the TFPT is also makes completes our portfolio with another thin film resistor based. Again, it's a PTC behavior, but it's a thin film based technology. So what is important for Vishay products here on these applications? When we are measuring, or when our designs are measuring the temperature, they want to control the temperature. They have big questions regarding the stability, how about the reliability of the measurement and things like that. So what we propose is really an important point, that a very high stability. by the time of your cars, of your two-wheeler products, they have to measure the temperature always the same for the whole part of the year. So stability, the drifts on the resistance value, controllable drifts on the resistance value along the lifetime of your components are very important, and that's why this is our first solution to the market, to the designers of those temperature sensing and control units, for example, in a battery with our NTC SMD or our several leaded parts. You might ask, oh, I need a fast time response. I want my circuit to react fast to the temperature changes. This will be a very interesting product to go very fast. It's the fastest, we have the fastest leaded components in our portfolio. If you look to these type of what we call it assembled products, the total production to total solution to the customer, there our main advantage against the competition is not only the solution customized according to designers' questions, it's also about the high insulation voltage, because these type of products, like you see it here, they are used in the elevated voltage areas. We need to put high insulation, we need to guarantee the high insulation voltage for the function of those products. So if we go through all these products one by one, you will see that NTCs, for example, NTC SMD, the surface mount thermistor, it comes with several, of course, with several resistance value and several sizes, but also they have a very special character that they have automotive grade. So it's they have a special ACQ 200 qualification. They have UL qualification. And then as we were just talking about the NTC SMD's competitive advantages, when you mount those devices on your PCB, so ours has a special terminations on those parts, so they are very flexible in those terminators, and it gives you a special bending characteristics. So these are leaded components, and this has, thanks to these special wires we have, they have the lowest thermal conductivity in the market. And you can see also that they have a very small bead size, which is 1.6 millimeter diameter. So it has an excellent response time in air, which is less than 3 seconds. So when your application requires a fast response, then you have to take this product. Another product that will be interesting on, for example, on a battery system where there are big bus bars, or if you have an inverter, a DC-DC inverter, or you have a braking system where you have to mount an NTC with a screw, like in this example, we have different type of mechanical executions. You can go through and then screw your NTC and have a great measurement and reliable and accurate measurement by having on a flat surface. It's one of the fast growing are again AC2Q, ACQ2. Is they can go up to 5 kilovolt AC in terms of insulation voltage. These what we call the lock types come with a very different execution. So we always recommend our engineers, our customers, to think about their design challenge. If they are looking for a better like 02A from Vishay, if they are looking for a high temperature, a high temperature meaning here in this case 150 degrees C. They have to go to NTC ALAC01T. We have also for an integration and customization, we have also some what we call assemblies, more like you can even have two lugs connected with a special connector on it. So we are very open to the design challenges of our customers. We are ready to talk with our customers and find the right solution electrically and mechanically in this case. We also understand that there are other possibilities in an EV. Think about it, there will be vibrations, there will be different requirements, as we just mentioned about the high voltage insulations. These are all come with a certain solution on the mechanical side, not only on the electrical side. So the Vishay's advantage, we try to make different mechanical executions on our NTCs or on our PTCs to make it a real solution for our customer. Another important product we see more to take place in a charging circuits or discharging circuits. So we have a pre-charge or discharge circuits. You have this inrush current, which can really make a problem in your designs. So one of our Vishay solution for these problem is a PTC inrush current limiter. So these they go and they withstand the high direct voltage up to 1000 volts. Inrush power cycle withstanding more than 100,000 cycles. So these are important for most of our customers when they are designing a discharging circuit, for example. What I would like to conclude my presentation is that Vishay nonlinear resistors, NTC, PTC thermistors have also a lot of tools for the designers. You can, if you go to www.vishay.com, you will see the NTC curve computations, SPICE models for different applications, technical notes and applications notes. You will see the links over there. You can go there and learn how our solution to your design challenges are. We have also 3D models where you can download directly or on your design, on your own 3D models of the whole assembly. So we are here to help you on your designs with the thermistors when you are using it in the EV, e-mobility solutions. Vishay thermistor, and we will be always happy to support you with our Vishay thermistors. Thank you very much for your attention.
Thank you so much, Gulshan. That was a really, really informative session. Thank you once again. Up next, we do have Mr. Adrian Michael with us, who is the Product Marketing Manager, Automotive Vishay Beishlak, who has been dealing with power resistors for over 4 years. He has a diploma in engineering and also served as a development engineer for battery management systems, DC to DC converters, and traction inverters at Exelon, Germany. Before I hand over the session to Mr. Michael, just a small reminder to all our audience out there. We definitely appreciate you being a part of this webinar and would love to take any questions that you have, but kindly please post them in the Q&A module near the chat box that you find at the bottom right. And with no further delay, I'd like to welcome Mr. Adrian Michael, who will be addressing the topic Gate Resistors in Power Applications by Vishay. The floor is all yours, Mr. Michael.
Thank you. Thank you for the nice and kind introduction. I will share my screen. Please let me know if you can see it also in the presenting mode.
Yes, it is. Thank you.
Perfect. Great. So let us start. So this is a quite a difficult topic, so I would like to give you some insights how to select the right gate resistor for power applications, because the gate resistor is influencing a lot of different factors, and I would like to explain on which factors we have to take a deeper look. And so let me go to this first slide. So basically the gate resistor is placed in front of the IGBT or power MOSFET. Here you can see the basic schematic, and we do have 5 different kind of influencing factors. First one is that the gate resistor is able to limit the peak current to protect the driver output stage. The second one, the gate resistor should be able to dissipate the power in the gate loop. Then with the gate resistance value, you can select or adjust the switching speed. And finally, you'll be able to handle the EMI capability of the schematic. Then the gate resistor to be chosen very carefully to prevent gate ringing effects and also to avoid parasitics turn on behavior of the power MOSFET or IGBT. And finally, we would like to give you some tips and tricks for your design to selecting the right gate resistor as well as the right technology for the gate resistor. Going into a little bit more deeper into the application. So finally, the gate resistor is located between the output of the power IC and the input of the power device. Yeah, and it's commonly labeled with RG. So the G stands for gate and the R for resistor. There are several kind of gate resistor concepts into the market. So mainly we see 3 different kind of concepts. I would like to explain you in detail a little bit more. So the first one is you have only one gate resistor for both switching cycles. So for the on and for the off switching, as you see it here in the first picture, and the switching on and off to follow the same timing. So the gate resistance value is constant for both. So that's why the switching for on and off is also the same, following the same timing. So the second one is the separation of the gate resistor into 2 different. So you have one gate resistor for the on switching and one gate resistor for the off switching. Here you are able to following different kind of timings, because for the adjustment of the on resistance value and the off resistance value, you have different kind of ohmic values, which finally leads into different kind of switching timings. And finally, a multiple count of gate resistors for on and off to split the load of continuous and pulse into different kind of resistors. So coming to the first effect, or to the first evaluation, so gate charging and discharging. So the gate resistor itself has to withstand a peak current, yeah? And the gate driver IC's output stage has a maximum allowed peak current values for turn on and for turn off, which is specified into the IC datasheet. When the output current of the driver IC is higher than the peak current value, then the output stage of the driver IC can be damaged. So that's why the gate driver resistor has to select it very carefully to ensure that the output of the driver IC is not damaged. Then the second one, the power dissipation. So the gate resistor has to limit the dissipation in the driver IC's output stage. A higher resistance reduces the current due to reducing the power of the dissipated in the driver IC. So coming to switching speed and EMI or EMC regulations. A higher gate resistance value can be beneficial from the driver IC's loss situation in thermal point of view. So the gate resistance will influence the switching speed of the power device, which will have finally an impact into 2 directions, efficiency and noise. So this means finally, with a higher gate resistance value, the switching speed of the power device will decrease, and with a lower resistance value, the switching speed will increase. Yeah, we're getting much faster. But finally, this is also leads into the loss situation. So the loss situation for a higher gate resistance value increase as well. And with the selection of the gate resistance value to the lower side, you will also getting higher switching speed, but finally also getting a better efficiency of the complete system. So the gate resistance value has to be selected really carefully, since the EMC regulation must be fulfilled as well. So you see a lot of different kinds of topics has to be involved to selecting the right gate resistor. Going into the gate ringing effect. So gate ringing is a quite often observed phenomenon due to the parasitics you have in your schematic along the gate loop. To avoid the ringing effect, one important measurement is to limit the parasitics here. So the parasitics inductance as well as the parasitics capacitance you have to limit in your schematic as well. So LP and CGE form a kind of a resonant tank, which can finally lead into a ringing effect. And a good solution here is to shorten the trace length of your design. So to place the gate resistor as near as possible to the power device and as near as possible to the driver IC. So as a rule of thumb, you have 1 nanohenry reduction by reducing to 1 millimeter. Finally, the parasitics turn on. Parasitics turn on is also a phenomenon in many situations that is a physical effect due to the high dV to dt value combined with the parasitics Miller capacitance here in the schematic. As a sketch in the figure, a high value will generate a displacement current IDS through the Miller capacitor. So which finally leads into a triggered paired device in half-pitch topology. So now looking into the influence factors I give you in quite short kind of amount of time, I would like to give you as well as some kind of design tips and tricks. Yeah, we take a look into the presentation that pulse handling and continuous power for gate resistor is kind of a really necessary factor to be into consideration. And one final need we do have is to get all these parameters out of the MOSFET or IGBT datasheet. So you will get out all these switching threshold voltage, all this frequency, as well as the driver voltage, including the internal resistance of the power MOSFET. With the selection of the external resistance values and the ambient temperature, which are specified by the customer, you can calculate back the peak power of the gate resistor as well as the average power which is applied to the pulse frequency for the on and for the off cycle. We as Vishay developed a kind of a tool which helping our customers to put all this kind of information with our support into this Excel sheet, as you see it here, and calculated by themselves all the necessary information out of this within this tool. So you will get a kind of continuous power. Here in this example for the on switching cycle, it's 70, kind of a pulse power, it's 78.13 watt within a amount of, or within a time of 0.12 microseconds transformed into a rectangular pulse, as well as the applied continuous power with 150 milliwatt. With this kind of information, you are now able to go into the data sheets and take a look which kind of resistor can be used in your application at 105 degrees C, which was a customer requirement. So in former times, you have to check both values in the data sheet. So you have to check the continuous power, as I told you, 150 milliwatt, for the gate on resistor. For the gate off resistor, it is in that case around 220 milliwatt. And now check into the datasheet values if this component is able to handle this continuous power. First of all, this is the first step. But if your ambient temperature is higher than 70 degrees C, you have also to implement a derating factor, which is highlighted in the derating graphs. So you cannot use these values anymore. You have to transform it via the higher temperature with the derating factor. And now you have, first of all, one case size you can use in your application. But this is only one step. The second step is you have also to be ensure if the gate resistor can handle the pulse requirements due to the requirements you have. Yeah. So first of all, you have to go with the calculated pulse power and the pulse time into the diagram and check again if the resistor is able to handle it. You can imagine this case of analyze is quite difficult to do it for more than one or two resistance series because you have to check it for each series again into the datasheet. That's why we developed the kind of guidance and Excel sheet again, which putting out you how many components you have to use to fulfill these functions. So in this case, there are our main, on the left side, highlighted our main gate resistance series we see in the market, which are used there. Here you will find the case sizes splitted by chip case sizes as well as MELF case sizes. And then finally, you will see here how many components you need to fulfill these functions. So first of all, the components you need to fulfill the continuous power requirements, as well as the components you need for the pulse handling capability. So if it is highlighted here a 1, this means that one piece can handle both. Yeah, so they can handle the pulse handling as well as the continuous power. So there's a little bit more selections out there. So on the left side, you will see it only for the on resistance values, and on the right side only for the off. And then there's a different kind of modes. So you can apply more power on different kind of series, which are specified into the datasheet. But this is going too much in detail. Then we talked a little bit about continuous power and pulse handling capability, and this is a kind of a nice overview to give you some hints and which kind of series is able to handle, or which kind of technology is able to handle which kind of pulse power. And for standard thick film chip resistors, you will see that the pulse handling capability is not as good. Going into special thick film chip resistors, it's highlighted here with CRCWHP, which is a double-side printed thick film chip resistor, which is almost handling 5 times the continuous power. Going into the MELF resistors, you also see a video in before for carbon MELF, which are able to handle much more pulse power. So now we selected the resistor in terms of continuous power and pulse. Now we have to take a look what is happening with the resistance value during the application. So this means during the heat in the application, during the pulses we see, and there's a phenomenon. So we have to take a look about the drift behavior itself. So finally, you selected a resistance value of maybe 2 ohm. And now over the lifetime of the application, the 2 ohm is drifting to 3, 4, 5, or is drifting to 1 or 0.1 ohm. And to be ensured that our gate resistor is every time constant, I will give you also some hints here. So the aging of the gate resistor causes a variation of loading and unloading times of the gate. So if the resistance value is drifting, your switching is not as correct as you would like to have it, which finally influences the switching times. So to get a sum of rule, if the ohmic value getting higher, the switching time decreases. which means that the switching losses occur in increased temperature in the IGBT or power MOSFET. Or an increase in switching delay times occur, which leads into lower efficiency. So we would like to build up high efficiency systems. That's why this is not acceptable. Another way around, if the switching time increase or the ohmic value getting lower, you're getting some trouble with the EMI, or in worst case conditions, your switching behavior for the B2 and B6 switches are not as good, so that 2 MOSFETs or 3 MOSFETs are switching on at the same time, which can finally damage the MOSFETs. So, and to get a quick overview, there is some kind of worst case drift evaluation for different kind of technology I would like to show you. So 1% thick film chip resistor with a TCR of 100 ppm per Kelvin will drift over 10,000 hours around 6%. So 10,000 hours is more or less equal to 10 years. So, and if this is not acceptable, normally we see requirements for 1% over lifetime. You have to switch to a different kind of technology. So here, thin film chip with TCR 50. If you're doing a worst case calculation there, you will see, okay, you can reduce it by almost 4% to 2% finally, but this is still not enough to fulfill the requirements. So the need is to go to a tighter specified thin film chip resistor to 0.1% TCR 25, and you will see you're getting a drift behavior over lifetime from 0.5% around, which finally leads that the specification are fulfilled. To sum up all this topic, so gate resistor driver circuits we see almost everywhere in each kind of application which you have to transform DC to DC or AC to DC or DC to AC. I would like to give you some basic applications. So DC-DC converters, onboard charger, wall charger, power inverter, drive inverter, PTC heater, E-fuse, circuit breaker, e-compressor, and DC supercharger. And on this side here, there are our main gate driver resistance technologies you will see in the market. So sorted by the pulse handling capability. So thin film MEMF resistor are the pulse handling stable part in the market, followed by thin film chip resistor, which are do have a quite tight drift behavior, and followed by thick film chip resistor, special ones which are special produced to withstand pulses. So in generally, what is the benefit out of this? So you have a good pulse handling capability for dynamic ranges. You can reduce the drift behavior over lifetime up to 5%. You saw it in the diagram before. You can reduce the component count, which finally leads into better stability and reliability, and as well, you can reduce board space. So thank you. Hopefully this was not overwhelming in such a short time. And I will give back to Sharon.
Thank you so much, Mr. Michael. That was a really great session about gate resistors. And thank you for the tips and tricks as well. I'm sure they would be beneficial to all our audience. Up next, we now have Mr. Clinton Stifler, Product Marketing Engineer, Vishay Dale Electronics, whose area of expertise is on surface mount power metal strip resistors. He holds a bachelor's in electrical engineering and has previously served in various capacities with companies focusing on equipment automation and LED billboards and lighting. As much as we await to hear you speak, Mr. Stifler, just a small reminder to our audience out there, we do see questions pouring in, and that's really great. However, please post them in the Q&A module and not on the normal chat. And with no further delay, I think I'll hand over the session to Mr. Clinton Stifler as he addresses the topic current sensing in EVs by Vishay Dale Electronics. Over to you, Mr. Stifler.
Perfect. Sharon, thank you for the introduction, and thank you for all the participants for joining and listening in. So I will share my screen. If you could see it, please let me know.
Yes, it's fine, and it's in the presentation mode as well.
Perfect. So I will be reviewing the current sense resistors that can be used in electric vehicles. I work with Vishay based in Columbus, Nebraska. So what is a current sense resistor? Oftentimes you will hear it referred to as a shunt resistor. The criteria for these are usually a very low resistance values, sub 1 ohm. A low TCR, a very tight TCR, and tight tolerances. So we have many different technologies for this product, including the power metal strip, which we will go more in depth to. And that is that zigzag pattern, that uncoated, that first one at the top. That's a picture of that. And then we have thick film, foil on copper, foil on ceramic, and wire wound. So these resistors can be used anywhere that a power supply is needed: inverter drives, motor controls, battery management, power factor correction. So what makes the power metal strip different? So the construction of the power metal strip current sense resistor consists of an all metal welded structure with a solid copper terminal, which is electron beam welded to a low TCR resistance element. So unlike thick film chip resistors, this construction does not depend on a ceramic substrate. The element is thick enough to be self-supporting, which means the resistor element mass is substantially greater than that of other current sense technologies. So therefore it provides a superior pulse performance by absorbing more electrical energy before reaching a temperature limit. Also, the resistance element is more robust than other technologies and can tolerate higher temperatures. It's also laser trimmed to value for a very clean cut. Other trimming technologies such as abrasion can create tampering edges in the resistance element, which can cause harmonic distortion or circuit ringing. And laser trimming also allows a wide range of resistance values without having to order a custom product. So you can get the resistance value you need for your design instead of compromising on performance with a value that is just pretty close. One thing, especially with the construction and how we vary with the power metal strip versus thick film technology, so I want to make sure to hit on this because it is large in automotive and EV applications, is the Cte mismatch. So as a material temperature changes, the dimensions increase or decrease slightly as it expands or contracts. The temperature change can be a result of environmental change or caused by continuous or pulse applied power. And duty cycled or pulse applications, when power is switched on and off and on and off, it causes a repetitive heating and cooling or expansion and contraction cycle. These events can create a long-term reliability concern for the solder joint of a surface when there's significant difference between the rates of geometric expansion. So the different rates are the mechanical interface are sometimes referred to as Cte mismatch or coefficient of thermal expansion. So the solder provides the electrical and mechanical interface between the circuit board material and the mounted device. In the case of the ceramic chip resistors, the FR4, the rigid ceramic, has a CTE of 5 parts per million per degree C, and this does not expand and contract at the same rate as the FR4 material at 15 parts per million per degree C, which applies a shear stress to the solder joint. Over time, the stress causes work hardening of the solder alloy, causing embrittlement, and then fatigue stress cracking, which you can see in the bottom right corner, which can lead to resistance value change in the connection or failure. So because of the Cte mismatch and the solder joint fatigue issues of the ceramic chip resistors, automotive designers have rules to limit their use to only smaller sizes, such as 0805 or smaller terminated footprints. Now the WSL, all metal welded construction, has a CTE of 13 parts per million per degree C. And because it does not depend on the rigid ceramic substrate, it has a rate of expansion that is more comparable to the CTE of FR4. Since it does not have a large CTE mismatch as compared to the FR4 material, it has better long-term solder joint performance And for this reason, the WSL product has been chosen in automotive applications in the larger, higher power footprints, such as 2512, 2010, and 1206 sizes where ceramic is forbidden. So with the all metal welded construction, these come with a higher pulse capability. So we have an online pulse calculator that you can get to by going to Vishay.com and searching Jewel Wizard, one word, into the Vishay search bar. So this will take you to the online pulse calculator that allows you to select the product series, enter the desired resistance value, and modify the ambient temperature conditions. Then you can compute a part-specific pulse capability and reference part number. There's also an option to change the chart between energy and power, whichever best suits your needs. The chart consists of 3 zones to display the capability curve over time. The first zone is defined as the pulse, which is generally less than 20 milliseconds. This is a short transient that is caused by a temperature rise in the resistance element. The transient is too fast to dissipate to the surroundings, so the energy is limited to the mass of the resistance element and the thermal limit. As the pulse duration extends into the surge region of time, the energy can transfer to the terminals. This increases the mass available for dissipation, and so the energy capacity increases, period. And the last zone is known as the short time overload rating, which defines the maximum energy capacity for the part, including the circuit board. Now we have different chip sizes for the WSL, including WSL, WSL-18, WSLP, and WSLP-18. And these can increase power density in a design in 2 different ways. So first, if we follow the colored bars through the other series, you can see that the power rating increases as resistor size decreases. So if you take the WSL 2512, for example, at 1 watt, if you go to the WSL P0805-18, that's 1 watt. So if it fits within the resistance value, you can lower your footprint and keep the same power rating. Second, is the red boxes illustrate that by changing series within the same size, you could progress to higher power ratings. So if you wanted to stay with a 1206K size, you have the ability to go from 1/4 of a watt to 2 watts. Now, the power metal strip technology extends to many other series that provides the same benefits of the all metal welded construction. As a result, these series have the same performance traits of high pulse performance, low resistance value, low TCR, low thermal EMF, and a tight tolerance. Most of the current sense resistors in these are laser trimmed to value like we discussed, and they have a tight tolerance, which provides design flexibility without having to be custom. So we offer a wide range of power ratings up to 10 watts for the WSHP. We have a wide resistance range from 1 milliohm to 1 ohm for the WSR. We have the Kelvin termination of the WSK, which provides better TCR performances and tolerances down to 0.1%. And then we have the high temperatures of up to 275 degrees C for the WSLT product. So the Vishay Automotive grade, which was playing in a video if you were in the session earlier when Vishay had the videos playing, the Vishay Automotive grade rating for these products means that they're qualified to AEC Q200, and they have additional quality requirements and control to assure a robust performance. And the data is available upon request that will support lifetime performance projections in your current measurement circuits. So going into some of the products we have here, so many designers are familiar with using a 4-pad layout for a 2-terminal device to provide a more accurate current measurement compared to a standard 2-pad layout. But one of the things it's not able to do is to improve the TCR performance of the component. The TCR, the temperature coefficient of resistance, is a combination of the portion of resistance from the resistance element and the resistance contribution of the copper terminal. Now, we prefer the greatest portion of the total resistance be dominated by the low TCR resistance alloy compared to the high TCR copper terminal. However, as you approach these lower resistance values in sub 1 ohm, the copper terminal becomes a larger contributor to the total resistance, so the TCR for the resistor becomes higher. A 4-terminal Kelvin connection is notched to remove a portion of the high TCR copper from the measurement circuit, and this improves the component TCR that could not be realized with a 4-pad layout on a 2-terminal device. The notch does not extend. The notch is not extended all the way to the resistance alloy because the copper terminal still provides a low resistance connection measurement in the current channel passing through the resistor. So the notch height is determined based on trade-off between the measurement accuracy and the enhanced TCR performance. So often designers are considering a low TCR from a standpoint of temperature stability with changing environmental temperature, but it also has an influence based on applied power, sometimes referred to as a power coefficient of resistance. So the illustration of the WSK 1216 indicates this notch construction, and the elevated construction of the series enables large resistance element. So the low TCR resistance alloy can have the greatest contribution to the total of the resistance value as compared to the copper terminal effects while still maintaining a compact footprint. So these current sense resistors are great for EV applications. These are our mid-size shunts uncoated. They do not have any coating like some of the WSL product that I was showing earlier. And they extend the power metal strip technology with construction that provides larger resistance element, lower resistance termination than is possible with the standard chip sizes. So these configurations enable low resistance values down to 0.1 milliohm while maintaining a low TCR. So everything with a blue border with the WSLP 3921, the WSLP 5931, the WSLF 2512 offer low profile for designs with clearance restrictions, but they also minimize the loop height above the board that minimizes the inductance. And then we have the Kelvin termination of the WSLP 4026, WSLP 2726, and the WSK 1216, which provide the best TCR performance of comparable resistance value of the standard 2-terminal construction. The very low resistance values of these series, as low as 0.1 milliohm, improves efficiencies by minimizing power dissipation. They also provide high power ratings to eliminate the need for parallel resistance elements, which can lead to measurement error caused by current flow in the measurement circuit due to small differences between the resistance elements when you're dealing with these low values. So these current sense resistors have demonstrated reliability for the broad range of demanding conditions defined by the AEC Q200 out to 2,000 hours in cycles, not the typical 1,000 hours or cycles. This is the reason that they're being designed by the biggest names in the automotive electronics industry for the conversion to electrical systems and EV hybrid systems. Another product that we have, this one is more customizable. These are the power shunts and the battery and meter current sense resistors. So you can see in the bottom right hand corner, this is a footprint, shows actual size. So these are larger resistors that have a high power rating of up to 50 watts and a high pulse performance. So these are great for automotive and EV applications. Any new designs that are being used are using these. And as you can see with the WSM BM 8518, there is customizable options to put a board in there to help measure whatever it is that you need measuring in that case. We also have the low TCR of the WSBS 8518-34, which has some notches, which again will help reduce the TCR of the copper contribution to the circuit. So these are great products for large power ratings up to 50 watts. So looking at electric vehicles, now we'll talk about where some of these pieces fit in. You can see that the core pieces are where a lot of DC to DC conversions are taking place. So we're going to be diving into those a little bit more. Looking at the onboard charger, you have the AC coming in, the PFC controller, the boost phase, the DC to DC controller, the full bridge switching phase, the rectifiers, and the high voltage battery. So you're going to use a current sense in each of these leading to the DC to DC controller, and all of the DC to DC controllers, whether it's AC to DC or DC to DC, use sense resistors in the controller module. Same thing with the boost phase. Every chipset in the boost phase has a current sense resistor in it. We typically use the mid-size shunts or the uncoated shunts because the needed requirements are a low resistance value, high pulse application, and a high power sense resistor is also needed. So for the low power applications, we have the WSLF 2512, which is up to 5 watts or 100 amps. And for high power, we have the WSLP 5931, which is up to 15 watts and 387 amps. So this is an example of a Vishay DC to DC converter, which is a 3 kilowatt 48 to 12 volt bidirectional design. It's a 6-phase topology, and on each phase you can see that there are 2 current sense resistors used, and for these we use the WSLP. If we look at the topology of the converter, we can see that the phase driver and each of the phase drivers requires 2 current sense resistors. So on our design, we use the WSLP 3921 2 milliohm and 0.5 milliohm because the ultra high power, low value, minimal current loss, but good feedback to the multi-phase controller. Now, if we look at the 48 volt to 12 volt converters, if we look at the buck boost converters, they all require high side and low side current sense resistors. Typically, we are using a 4-terminal topology or an ultra high power WSHM or WSHP, which ranges from 6 to 10 watts at 5 to 100 amps. On the low side, where the current requirement isn't as high, we can use a smaller 4-terminal Kelvin connection, WSK 1216, which feeds back into the control unit. And if we look at the high voltage side, we have a similar topology. You have the buck LDO and the DC to DC, and the typical requirements are the smaller current sense resistors that we have discussed. When you were looking at the input from the full bridge to the rectifier, typically you have an inline battery shunt. Same thing on the output to the 12 volt and the inline battery shunts that go along with it. So the difference in requirements will be your high amperage requirement. So we look at the 30 watt current sense resistors, which need the battery shunt, the WSBS product. The others are typically lower in amp requirements, so you can deal with the smaller current sense resistors. You can get better sensing accuracy out of the 4-terminal devices, as we've discussed, but it will obviously depend on the design that the customer ultimately wants. The advantage of the WSHM is that we can get high power resistant values. So if the customer is looking for a system that requires 100 milliohm, the WSHM is the route to take. If they need 5 milliohm or less, the other resistors will be able to fit the bill. And briefly, just looking into some of these as well, the WSLP 3921 and 5931 offer the lowest resistance values of the surface mount power metal strip series down to 100 microohms. They also offer the highest power rating of 15 watts. This performance envelope is often necessary for battery management systems, high power traction inverters, motor control, and 48 volt automotive applications in electric vehicles. The WSLT series extends the temperature range up to 275 degrees Celsius, and this allows for devices to be used in gallium nitride inverter modules or high temperature under the hood applications. And then the WSK 1216 is the one that we discussed a little bit, which features the 4-terminal Kelvin termination to offer a more accurate and repeatable current measurement and the best possible TCR for devices with the resistance of 1 milliohm and below. The series is currently available down to 0.2 milliohm, and it will offer a very low TCR value of 50 parts per million, providing superior temperature stability for high current measurement. The 8-watt rating in the 1216 footprint offers the highest power density of any current sense resistor. So this series is ideal for automotive applications such as electronic braking, the power steering, to reduce the vehicle weight and improve reliability. Now, the WSLP 2726 and 4026 offer extremely low resistance values down to 200 microohms, offer high power ratings, 12 watts, and the benefits of 4-terminal Kelvin termination. So again, the 4-terminal Kelvin termination improves the current measurement accuracy and repeatability and provides improved TCR performance over a 2-terminal construction. The low TCR performance offers more stable current measurements over an ambient temperature range, and also the temperature increase due to applied power. The 2726 configuration offers the benefit of a smaller footprint, while the 4026 allows for automatic inspection of the solder fillet. So these series provide improved accuracy in battery management systems, as well as dynamic braking and power distribution safety switches for 48-volt automotive applications in electric vehicles. So the WSLT series, again, extends the temperature range to 275 degrees C for the high temperature under the hood applications. And then the last product we want to hit on is the WFM, which provides a wide resistance range and a high power rating that enables a much higher power density compared to the standard chip resistor sizes, and it has a lifetime stability of 0.1%. So often when power density increases, the trade-off is that the changes in resistance increases with time, but not with the WFM because of the resistance alloy and the heat spreader construction of the part. The combination of the power density and stability makes an ideal choice for automotive applications that require stability with limited board space. So these include transmission controls where changes in resistance can cause hard shifting between some of the gears as the electronics age. Now, one thing I want to make sure to talk about, because we threw a lot of information at you today with all of the presentations, but the data sheets is often what the designer considers when choosing a resistor or any of the components, right? The data sheet for the Power Metal Strip series makes it easier to find deeper information through the links and additional resources, which include 3D models, brochures, and additional documents related to the product. It also provides an easy connection to the technical context that are specific to that product. So this link is found on all Vishay data sheets. So all of the products that you heard today, if you look on the Vishay website for the data sheet, there will be a technical questions contact email address at the bottom of it, and it will go to individuals like myself or the other presenters that will be able to answer more technical questions. So if you have any questions on these products, just go to the part specific data sheet, and that email address will put you in contact with the correct individuals to help answer your questions. And that is all I have for today. Thank you.
Thank you so much, Mr. Stifler. It was so good to hear you speak. And thank you once again, Ms. Armagan, Mr. Michael, and Mr. Stifler for all your valuable inputs on nonlinear gate and current sensing resistors. I think it's really important, especially with EVs being a massive hit, if I may say. And as of now, the floor is now open for question and answers. Just a reminder again, please do post it via the Q&A module. We do see many questions coming in and the chat. Please make sure that you select the Q&A module while you're posting your questions. And if it's fine, we would have Ms. Armagan, if you could pick up the first question, and then Mr. Michael, and then Mr. Stifler. Would that be okay in terms of answering the questions?
Yes, for sure.
Yeah.
So here we go with the question and answers. You could see it in the Q&A icon on your screens at the bottom. You'd be able to see the question.
Yeah, I am able, and I have seen one which is related to right now for pre-charge circuit, which is better shunt or PTC. It's a very nice question. Thank you for that. I can say for the PTC, we have a very good energy calculator. Depending on the energies you have to absorb on the PTC, by using this calculator, you can choose if a PTC a good solution. So our colleagues can send you the energy and inrush current limiting PTC calculator to you. No problem. But it all depends on the energy levels.
Right. Thank you. Mr. Michael?
I'm not sure if I'm getting the question 100% correct, but I think the question is, what is the temperature versus the efficiency behavior? So generally, it is so that due to the higher temperature, a resistor will increase due to the TCR effect. You have it into the resistor, or will decrease because the TCR is specified with plus minus, so it could be going into two directions. And if we learned that the resistance value have a 100% effect on the switching behavior of the IGBT or MOSFET. So if the resistance value getting higher, your switching speed will decrease, which finally leads into lower efficiency. Or counting that back, if your resistance value getting lower, your switching frequency will increase, which finally leads into a better efficiency, but also into a worse EMI conditions. So this is not 100%. You cannot say which is better. So normally you have to ensure that your resistance value getting constant over the complete lifetime, that you have all over the conditions the same behavior of the resistor and the same behavior of the switching.
Excuse me, can I come back to the question from Pratik, which Gulshan has answered partly? For pre-charge circuit, which is better, shunt or PTC? So the answer, Gulshan explained about PTC to handle the inrush energy, and the shunt is used to measure the current. So these are the devices used for totally different applications. And as you may know, shunts are normally having a very low ohmic resistance value. And for the energy handling, the PTC or a resistor would have a higher ohmic value, typically more than 100 ohm. And shunts are in the range of milliohm or micro ohm. Thank you.
Thanks. Bye-bye.
Mr. Stifler? Any question you'd
Okay,
like?
so I'm seeing a couple in here that Brian has answered, but just to hit on some of them. So we talked about the current sense resistors being able to withstand high temperatures, but there was a questions about low temperatures as well, and potentially in satellite applications in space where the low temperatures will come into play. So they do withstand down to negative 65 degrees Celsius, and that is included in qualification data that we have. They have been used in a lot of or some space applications, specifically the ones that we discussed. And we do support source control drawings for upscreen testing if there's any certain requirement that needs to go above and beyond what is done now with the AEC Q200 and the Vishay Automotive grade. When we make something AEC Q200, that's the AEC Q200 standard is typically to 1,000 hours or 2,000 cycles for testing. And then the automotive grade extends that to 2,000 hours or 2,000 cycles. So any product that we release has AEC Q200, we do it double. We go to 2,000 hours or 2,000 cycles to hit the Vishay automotive grade standard. So we don't want to meet just the bare minimum that some competition will use. They will tell you that they are AEC Q200, and some of the data might be a little bit more sparse to find. But with our products, we test them to 2,000 hours or 2,000 cycles with the Vishay automotive grade standard, and you can find more information about that with the data sheet links as well.
Thank you so much, Mr. Stifler. Back to Gulshan. Any other question you'd like to answer?
I see a question from Nitish. So why most automotive circuit using NTC and not PTC? It's also a very nice question. NTCs are used mainly for the temperature control, sensing, and measurement applications. Since they have high resistance value, they can measure the temperature in a very accurate way. PTCs for sensing is limited because of their technology and because of their resistance values. I hope this answers the question of Nitish. If not, yeah, I'm willing to discuss further.
Right, just a reminder to our audience as well that any questions that are not answered will be followed up by Vishay after the Q&A session. I'd like to pass on to Mr. Michael or Mr. Stifler if you all would like to pick up any question and answer it.
Yeah, I will go for one. Nowadays, I will read it. Nowadays, the EVs are catching fire, and we know that we have the sensors for determining temperatures even then why they are not able to cut off the power supply from the source in order to prevent from short circuit. So normally, if we measure the temperature of the battery as well as some other topics, for example, the voltage level as well as the internal resistance of the battery itself, you can really determine how healthy the cell is and can cut off the charging devices. Nevertheless, there are some chemical reactions ongoing into the cell as well. So you might know that you have a separator in between the anode and the cathode. And if the separator is damaged, no kind of measurement device is able. So up to now, no kind of measurement device is able to detect this. And this will lead into an internal circuit of the cell, which cannot be measured by a battery management system, for example. And this finally leads into a short circuit of the cell. But nevertheless, there are technologies developed in the market which are using different kind of anode and cathode materials as well as separators, which are preventing this issue.
Thank you so much, Mr. Michael. Mr. Stifler.
Yes, there's a question about what is the maximum plus minus temperature ranges for these shunt resistors. So typically with the WSL product, the standard, it is from -65 degrees Celsius to plus 170 degrees Celsius. Now with the WSLT product, it extends the temperature range, so it will still be -65 degrees Celsius, but it will go up to plus 275 degrees Celsius. So if you have demanding under the hood applications where the higher temperature is needed, the WSLT series is going to be the best fit there.
Thank you. Back to all the panelists. Any questions that you all would like to answer from the questions that have been posted? And to our audience, kindly post the questions in the Q&A module. We do see still few coming on the chat, but kindly please post them in the Q&A module. And I'd like to open the floor to Mr. Michael, Mr. Stifler, and Ms. Armagan to see if there's any question that you all would answer.
There's one I see regarding the lead time of the NTCs, PTCs, and we maintain stock in India. The lead times are quite competitive, and so if you need many specific questions regarding the Regarding our products, all Vishay thermistors, NTC thermistors, PTC thermistors, you can contact our salespeople. They will give you much more specific information about the lead times. And yes, we have stock on our distributors. Thank you.
I can take over another one. Is there any sensors coming which can detect the possible explosion and give us the warning indication? I know that some development at cell manufacturers going on that they would like to integrate an internal fuse into the lithium cell itself, which finally cut off the lithium cell out of the system, which prevent explosion at the end of the day.
Adrian, there is a generic question from Vijay. How do we reduce noise for a high voltage application in resistors? So we need to first ask what is the voltage level and what kind of noise they are concerned about. So Vijay, can you please elaborate a bit more on your question? Or you can put it in the chat box or email to us with more details. Then we can answer your question.
Yeah, that's very good.
Thank you. And any more questions that the panelists would like to answer? We do have few coming in terms of research going on.
Maybe I will take this one. Is there any research going on regarding very low temperature components? For understanding, normally our components, maybe all of our components are specified in the area of -55 degrees C. Normally, it will be enough to cover almost all applications. Nevertheless, for avionic, military, and space applications, we do have some products which are also specified with lower temperatures as well.
Yeah, it's the same for, yeah, I agree with Adrian on this. We can go down to -40 without any problem. Lower than that, yeah, it's case by case.
Couple of them are raising their hands. Could you all please post questions in the Q&A module, please? I think we have a couple of more questions coming in if you'd like to have a look.
I see Sanjay asking, IoT being emerging, what's the best components on smart solutions? What we see on the IoT for NTC sensors, yes, we see for temperature measuring, the surface mount devices, 0402, or we see what we call flex design. They are NTCs put on a very thin flex circuits that we see it in the several IoT applications in automotive or in consumer electronics for NTCs.
Mr. Stifler, Mr. Michael, any more questions?
Yes, so there's a question about sharing the various resistors available and list them and which are most preferred and commonly used at the moment. So I will share a link to an applications page on the Vishay website that will go into some applications and markets that the resistors are used in, along with some other products that will take you to a direct link for the data sheet. And then if you have further questions, you can reach out to the technical contacts as well.
Yeah, this is called Engineer's Toolbox
Yes.
on the Vishay website, and there you will find the most common used products within this application.
Thank you so much. That would be great. And I think we're almost done with the questions.
There's also one question again. Have you ever done a viable analysis for this product? I don't know which one is referred when it's called this product. What I can say for thermistors, yes, we do viable analysis regularly in our technical team.
Great, thank you so much. If the audience have any more questions, we have around 5 minutes. If you all would like to post any more questions, the panelists are here. All right, I think all the questions have been answered. Oh, there are still a few coming in. Would you like to take any questions? Sure, go ahead.
So with the reliability reports, you can reach out to us, and we do provide the qualification data, reliability reports, fit data for the current sense product.
Same to the resistors, the general resistor ones.
Yeah.
What's the life period for circuits and components? I would say more than 20 years.
More than 20 years, yeah.
Yes.
So I think this is a question to the organization team. Will be, as a participants, get a copy of the presentation?
Yes.
Sharon?
Yes, so regarding that, a certificate of attendance along with the recording will be sent to all our attendees in some time. And yeah. And also the recipients of the gift voucher would be informed shortly after the webinar via email. So those are the questions. Just a reminder that the Vishay team has told that they would love to answer your questions. You could contact them as and when needed. And any last questions you all would like to answer? Ms. Almagan, Mr. Stifler, Mr. Michael, Mr. Gopal.
There's again a question from Mohammed about IoT, and I have attached a generic IoT brochure in this chat box with a website link, and you can find several IoT applications with several Vishay products which are suitable for these applications. So please refer to that first, and then you can come back to us with your specific inquiry.
Perfect. It's really great. And suppose those were the questions, unless we have any. To those who, had problems with connecting to the session or were unable to, stay for the whole session, as long as you've registered, you would be sent as informed the certificate of attendance along with the recording. And I think there's a question on briefing on IoT app challenges, IoT application challenges. Will you all be able to answer that, Team Vishay? Anyone?
Well, one of the challenges I could think of is because these are low battery power devices, components, so they should have low leakage. They should have lower power consumption. And if we are talking about the integration with Bluetooth devices, so the range should be far enough so that these devices can communicate with each other. So when you talk of capacitors in IoT applications, they should have low ESR, low leakage current. If you are talking of resistors, they should be a good resistor, stable resistor with low TCR, tight tolerances. Yeah, so these are some general guidelines.
Thank you so much, Mr. Gopal. I think we're done with the main questions. Well, thank you once again, Ms. Armagan, Mr. Michael, Mr. Stifler, and all our attendees as well. We do hope this webinar has been beneficial for both the attendees and those who have presented in the webinar. And we would also appreciate your response to all our audience out there. We would appreciate your response. We would be sending an email along with a survey link shortly, and it would be really great to have your response in it. As informed, a certificate of attendance also will be sent along with the recording, and the recipients of the gift voucher, you would be informed shortly after the webinar via email. Thank you once again on behalf of EFY. Thank you, Vishay. Thank you, audience. And thank you all for being a lovely audience. It was a pleasure being your host for the day. And I do hope you'll have a lovely day ahead. Thank you once again.
Thank you. Thank you, everyone. Thank you, Vishay team.
Thank you.
Bye. Thank you.
Bye.
Bye.